My talk will be about tropical reduction and lifting, which is a way to associate compatible tropical and reduction data to certain analytic spaces, functions on them, differential forms, and so on. In fact, we'll consider two cases which are somehow surprisingly similar or analogous. Let me briefly start with the theory of K-analytic spaces. I'll use the also fixed notation. So in this talk, K is a non-Archimedean analytic that is complete and real valued, provided with absolute value from K to negative numbers. Field. Also, we always assume that it is algebraically closed. And we'll denote by K naught ring of integers. And by K tilde the residue field. Okay. Now we'll work with Berkovich analytic spaces. Berkovich K analytic spaces. Such an X is covered by affinoids, glued from affinoids. The AI just is a K-finite algebra, but is convergent power series with few variables. So far, I ignore radii, but we always work with strict, so-called strictly affinoid. So you can always choose radii for appropriate rescalings of coordinates to be equal to 1, modulo some ideal. And this guy can be described in two ways. First of all, as a set of all semi-evaluations, real semi-evaluations, that is multiplicative semi-norms on A, continuous, yeah, and agreeing with K, or one can also describe this as the set of bounded homomorphisms K homomorphisms to a K analytic, to an analytic field containing K. This time model equivalence. If two such bounded characters factor through a third one, we say that they're equivalent. So these two definitions are analogous to spectra of schemes. This is analogous to prime ideals. This is analogous to points characters. Description of ideals by the character. Homomorphism to field difference. Good. Now, just maybe one remark. We'll always work with curves. So our analytic spaces are relatively simple. Topologically, they are sort of infinite graphs, very branched. A good example is Bruatit's one-dimensional building. So it's something like this. Maybe with finitely many loops, maybe with some points which are a bit more special. Vertices of this graph, vertices are called points of type 2 by classification of points on curve by Berkovich. And any such X satisfies that its complete residue field, if we take its residue field, over K tiled is a function field of a curve over K tiled of residue field, which I'll denote Cx. And in fact, the branching locus at X, yeah, all directions outside of X, this is precisely the set of closest points of Cx. So we'll use this a lot. Okay, good. Now let's discuss a bit what do I mean by tropical reduction. So it happens often that to a geometry of K, one can associate geometry of K tiled. Typically, this is reduction, yeah, or closed fiber of a formal model, or one can associate a geometric object of a group of values, which is polyhedral geometry. Typically, this is tropicalization. Whereas sometimes there is a common topological information which is encoded both here and here. But the interesting thing is to combine them together in a compatible way. And this is what I am calling by tropical reduction. And here is the example. If X is a semi-stable model of a K-analytic space X is smooth and assume it possesses a semi-stable model, then by gamma X we denote the incidence graph of the closed fiber. Yeah, this is this guy is just SNC or normal crossing in general. Let's assume it's SNC. Yeah, okay, normal crossing. That's normal crossing. Normal crossing divisor. It has incidence graph, simplicial complex. Yeah, standard definition. And this gamma X is even a skeleton. It embeds into X and is a deformational. And now, the four guys one can associate to X as follows. Can associate gamma X is just something topological. One can associate gamma X plus induced PL structure. And this is a tropicalization. One can associate the closed fiber. This is, closed fiber of a formal model. So this is some geometric object over reduction over residue field. And one can combine them together in two ways. One way is to consider XS and add M vertical log structure. Log structure used by all divisors of which are vertical, which are located on closed fiber. So this is one way. Another way which we'll use in this talk is more ad hoc. One can take gamma X, this PL structure, and enrich it by some data from algebraic geometry over K tiled. In our case, it will be equivalent. Just this is sort of a bit more high level, high-tech level, let's say so. And we'll discuss two cases for tropical reduction. One when X is provided with differential form and residue characteristic is 0. Let me denote by P a residue characteristic of K tiled throughout this talk. Here P is 0. And the second case is a cover X to Y cover, which is the interesting case is when it is widely ramified. So here it will be larger than 0. And in these cases, it's not enough to use just log structures. I don't have any conceptual explanation what tropical reduction is and where it comes from. but I have some constructions, and there are lifting theorems which indicate that this is the correct construction. We are not really losing data when we are combining all these data together, but data is organized relatively. Okay, now let's start the following topic. It's called metrized curve complex after Amini Becker. Let me just say them curve complexes. For shortness, this was introduced by Amini Becker as an equivalent description of tropical reduction of curve. So let's also assume that, so now D is a curve. It's nice that is smooth, proper, connected, and let's assume that D is a divisor, just finitely many points. Now, we'll consider X as XD, a semi-stable model. So X comma D. X is a semi-stable model of X, but I also want ds to be equal to D and just contained in smooth locus of the semi-stable model. In a sense, this just means that on our model, D specializes to distinct smooth points. Yeah, also very standard notation. And when gamma X associated to this guy contains finite part, finite edges. I'll denote them in, say, UV. E will work with oriented edges. So we have tail and head, and UV generic points on the closed fiber. So we just correspond to components, and any such guy correspond to a node. Yeah, it might be self-intersection when U equal V, and it might be intersection of two nodes. And the length of this guy, length equal to minus log of absolute value of pi, where the node is locally looks like xy equal pi. Formally. Okay, good. I guess this is very standard. Pi is an element, yeah. Pi is an element of maximal node. Also, we have infinite legs, infinite edges called legs. We form UP. This time U is a generic point, and P on the component of U is mark point. Yeah, it contains divisor. And okay, length of such guy is infinite. Good. Now, this gamma X is embedded into X. And any U is a type 2 point whose directions are precisely parameterized by the component, normalized component of the closed fiber corresponding to this point. Okay, and now the metrized curve complex associated to this thing is the following. It contains of gamma X, and it contains of CU curves, smooth proper curves, connected curves of okay tiled, parameterized by finite vertices. And also there is a data that for any finite for any edge. It corresponds to a point PU on CU, just corresponding to the mark point on the component or to the node on the component. So strictly speaking, one also should provide such an information, identify edges with points on components. I'll not put it into the notation. It's always there. Good. It turns out that this is another equivalent way to describe logarithmic reduction, or a tropical reduction. Maybe just one last remark. If I take about the structure of X and relation to stable models, if I take X and remove vertices of the graph of the skeleton gamma X associated with the model curly X, this breaks down to disjoint union of open disks, annuli, and punched disks. Now, in fact, I have a map from X, reduction map from X to XS, reduction or specialization map. It pre-images of generic points, just single point of type 2. So I denote them by U here and there. The rest are pre-images of closed points. There are three types: smooth points, where pre-images are disks, nodes, pre-images are annuli, and punch disk, where pre-images of mark points. Mark points with removed closed point on the analytic curve. Yeah, so that's the reason why we get punched disk. Okay, good. And in fact, by the way, stable reduction theorem is equivalent to existence of such a set of points of type 2, one called triangulation of the curve. So it's a deep geometric fact about X where such guy exists. It's equivalent to stable. Okay, good. So this is all very well known, just to fix notation and proceed now. So let's start now the topic of differential forms, but I'll discuss functions first. So let's now assume that I'm given, and just to illustrate the same ideas, I'll start with functions. So let's assume that X is a curve. I'm given a function, a neuromorphic function on X. Yeah, or you can just think map to P1, by the way. It will be relevant maybe later. Now, we fix D, which contains zeros and poles of F. So D is large enough divisor, relative to A. That's it. And then we'll consider, okay, X is a semi-stable X and D, semi-stable model of X and D. Okay, now to F we can associate the following things. First of all, we can associate absolute value of F. This is a function from X to R large equal 0, continuous by the way. In fact, topology is defined in such a way that this is the biggest topology of the Berkeley space. Topology is the biggest topology, so that each such function is continuous, and it sends point X to just the absolute value of F, the value that corresponding to X, yeah, just compute the absolute value at F. Okay, now also for any point of type 2, we can do the following. We can pick up an element of K such that its absolute value is just the absolute value of F at X inverse, and then absolute value of Cx of X is 1. We can consider reduction of this guy. It's not 0 because of this condition, and we denoted f tilde at x. So it is it lies in hx tilde. So it's just a meromorphic function on the associated curve. Yeah, it is a meromorphic function on Cx. Good. Now we can associate to x and d and f. Yeah, so we start with xf, and such a guy helps us. Yeah, a choice of a semi-stable model of x and d helps us get the following tropical reduction data. We consider metrized curve complex gamma x, all guys CV. Yeah, this is just metrized curve complex of Amini-Becker. And when we add the tropical datum of f, which is absolute value of f restricted to gamma, this is a piecewise linear function on gamma, which is linear on edges. And we add also these reductions of f at any point u. Okay, also meromorphic function on each C. Now there are some compatibility conditions, but they're very natural. For any h from u to v, we actually have at the slope of minus log of, let me say just log f, PL e log of, let's say minus, okay, just log. No, I'll write minus log. So this is VPL. Logarithm of absolute value is PL function. Yeah? So slope of log f just equals to order along E. Yeah, and here we need orientation to say if we take in which direction we take slope. So it just equals to order at PE at the corresponding function of reduction curve at U of f tilde. So it's a meromorphic function. It might have pole or 0, and yeah, it corresponds to this. In particular, this implies that order, and usually I'll just write order of E by a slight abuse of notation. So order of E of FU equals to minus order of E op FB. Okay, so on different sides, these meromorphic functions have opposite order. And also for any leg, we have order of f at P equals to order of the reduction at the corresponding. So these are all compatibility conditions about f. They describe it very well when we map from x to P1 defined by f is tame, and this does not work well otherwise. We'll see it in next section. But now let's go to differential forms. And we want to imitate the same construction. So now we are given x phi. We consider any D which contains zeros and poles of the meromorphic differential form. We choose a model with corresponding gamma x and CV. tropical reduction of the model. And now the question is how to define reduction of phi so that it is informative. Okay, the idea is as follows. We should metrize somehow naturally the space of differential forms. In such case, we can imitate what I outlined just now for functions. And fortunately, there is a simple natural way to do it. So there exists unique maximal metric on omega x such that the differential is non-expanding. And in fact, one can easily describe it just by providing the unit ball, which is a subsheaf here. Let me say here. This unit ball is just sheafification of OX naught, d OX naught. Yeah. So these are all functions of norm less or equal 1, and these are all forms less or equal 1. Obviously, providing such a k naught submodel of omega x determines metric on omega. Okay, good. And second, one can now compute the reduction of with respect to this norm. And reduction, which is defined by this rule, is a union of skyscraper shifts sitting at points of type 2. And at each type 2 point, we get the following. It restricts to omega cx log on cx for each x of type 2. So reduction of differential forms is differential form. It's not so sheaf of differential forms, not so surprising, but a subtle thing is what we get here log. This is just differential forms on x twisted by sum of all points of cx. Yeah, so it's sheaf of logarithmic forms, but at any point. So it's huge quasi-coherent sheaf. It's not coherent. But okay, this is what one gets. As a corollary of this, such a function is defined. It is obviously continuous, but it's not continuous. Not continuous. But on each graph, finite graph, it is continuous and even PA. So it behaves well on finite subgraphs, but if you consider all directions, it's not. It's only upper semi-continuous. So it behaves quite differently from absolute value of f, but restricted to finite graphs, it behaves nicely, and that's all we need. Okay, good. And now we can imitate the same thing as we have done before. We can consider now tropical reduction, which looks as follows. We can consider here gamma x, the curves, absolute value of phi restricted to gamma x. This is PL function linear on edges. And also we can take here the reductions, the images of phi at any z. So these are just meromorphic forms. on CV. Okay, we must satisfy some compatibilities. Compatibilities also are natural. So slope of log of phi is log order minus log order at E of phi U tile for any E from U to V. Just same rule as we have seen before, but the order should be taken with respect to logarithmic. Yeah, this is just the order plus 1. Because we must compute our order with respect to this shift, not with that. So we compute logarithmic order of a form. It's shifted by 1. Similar compatibility holds for legs, just without any shift. Just compatibility for legs. Let me skip it. It's not so important for us. Maybe just from this condition, I'll mention that for such an edge, one has that order of phi tiled at E plus order of phi tiled at V, E op, equal -2. Yeah, the sum of log orders is 0, but sum of orders is -2. As often happens when one glues differential forms on nodes. So here this condition is conceptually explained in this way. Okay, good. Now one might hope that this is all, but that's not all. There is one more invariant of differential forms one has to take into account, and it is a residue. So if A is an annulus, yeah, so functions on annulus are just Laurent series, convergent Laurent series into variables. Yeah, so this is the annulus given by absolute value of t between R1 and R2. And then differential form on such guy is given by sum of I ti dt over t. I also use here logarithmic shift of indices. And when A0 and assume that phi has no zeros poles on the annulus, then first of all, resist n such that absolute value of phi equals to absolute value of an tn on the skeleton. So there is one dominant term. And second, A0, which I'll denote as residue of phi along A, is independent of coordinate. So it's an invariant. Okay, the proof is relatively well known for trivial valuations, and Laurent series is done by Sear many years ago. Anyway, it's proof is relatively elementary, and I guess this result also is not surprising. Properties of this residue function are also not surprising. So residue defines me a map from edges of gamma x. Let's say residue phi. I'll denote it residue phi to k, and it is harmonic. Yeah, condition like sum of all residues is 0 or null. Yeah, sum for any point of type 2, sum of a branch of x, residues in the direction of E of phi equal to 0 for any x of type 2. And if we are given a leg when the residue of phi at E equals to just usual residue of phi P, let me say residue phi. So it's compatible with classical situation at mark points. And in addition, if I consider residue phi of E, I rescale it by the scaling factor of U, and then take residue when this is the same as the residue of E of phi U. Just to recall, phi U is the residue of Cu phi. Residue at it lives in omega of Cu. Meromorphic. Okay, so all conditions are very expected. And then there is a theorem, Lifting theorem, which says that if, and by the way, so far, this holds in general no assumption on characteristics. So to define such reduction, you don't need anything. The question is if this encapsulates most of information of tropical and residual information about before. The answer is yes, if residue characteristic is 0. So if residue characteristic is 0, then any compatible datum like, sorry, this is malfunctioning. Okay, so I'll open it again. Okay, then any compatible datum gamma x, Cu, absolute value of phi, just a function, piecewise linear function of on x and reductions and the residue function lifts to a pair x and phi over K. So such tropical reduction datum can always be lifted if it's compatible, satisfies all conditions I listed, and the residue characteristic is 0. And this is not true if residue characteristic is not 0. So we definitely know that there are more invariants, and just these invariants are not sufficient. Good. Now let's go to the next question to covers. So in such case, I consider finite cover xy generically tied between two nice curves, and then there is a simultaneous semi-stable reduction theorem which says that there exists skeleton which contains all ramification points. Skeleton of x, and it is preimage of skeleton of y. So we'll typically, actually, this theorem is as difficult as semi-stable reduction. It looks more general, but it follows easily. And it does not give really new information about morphism, and it induces gamma f from gamma y, gamma x, gamma y, and also for any vertex u in gamma x and mapped to v in gamma y, there is a map cu to cv, which shall denote f tiled at u. So this guy and f tiled of u is a sort of a natural reduction, tropical reduction datum for F. Yeah, and indeed, it's more or less contains the same information about this map as you can obtain from the simultaneous semistable models, compatible semistable models, and logarithmic structures between them. Yeah, so it's just a way to encode this. Now we satisfy some very easy compatibility conditions, which I will not describe now because we are a bit out of time. Mainly about degrees, just about degrees and degrees of the maps, where the map has constant degree. On edges, the degree of the map on edges is precisely the dilation factor between edges. The map is linear on edges and just dilation by n, where n is infinite. Okay, and then there is a theorem by Amini, Baker, Bourgalet, Rabinov, that if the reduction, if such a guy is tame, that is, all maps, reduction maps, are separable, generically done, then there is a lifting. Again, if you give such reduction datum compatible, as I described or outlined, then you can lift. And it breaks down in general. So what can be done in general? One has to consider more invariants. There are more invariants. And here I can just give you one such invariant. It's called the different definition. The different function from x to 0, 1 is given by different at x is just the different of the extension h of x over h of y. It behaves very similarly to absolute value of differential form. It is PL on finite graphs. In fact, it has a natural description. Yeah, maybe I just should say this function measures, in principle, it's invariant of wildness of extension. It measures how much, this extension is wild. So it's 1 if it's not wild, and it becomes smaller and smaller if it is wild. And so in that case, it's trivial. It doesn't exist, but it's a tropical invariant for wild extension. Now, proposition says that, in fact, this function is absolute value of tau. For tau, a section of dualizing sheaf of f, which is just pullback of omega y dual tensor with omega x. And this tau corresponds just to the map from pullback of omega y to omega x, the canonical map from fundamental sequence. And in fact, this tau just measures how much the natural norm here, the norm of tau drops with respect to norm. And this difference is precisely measured by the difference. So it's natural to expect such a thing. So now I claim that this guy is naturally metrized just by pullback omega y naught, dual tensor omega x naught. So metrization of omega x and omega y give me metrization of the dualizing sheaf. And then any section has a natural norm, and this is precisely different. Moreover, we can now define the reduction For this, we should only compute the reduction of omega f, and not surprisingly, it turns out that if I take reduction at x of type 2, I just get omega x log, yeah, which is just a pullback of omega cy dual tensor omega cx. Yeah, y is f of x. So one can, using this, we know how to define for any, so from this, we can define a reduction of tau for vertices of the scalar. Good. And now, theorem says that if I associate to, let's say, assume that we are given a datum like earlier, gamma f, and reductions at points u, and the different function on gamma f, and the reductions of tau u, subject to some compatibility conditions, which I don't have time to say. I'll only say that these are conditions about slopes, something which relates zeros or orders of this guy in slopes of different, and a bit of restrictions on tau. It must be exact in some sense. I don't have time to say, but again, some simple conditions. Now, assume that we have such a quadruple with compatibility conditions, and it is minimally wild. That is, for any v in gamma y, or exist at most one x above y with inseparable f tilde x, and when the degree is precisely p. So the only inseparable guy is just Frobenius. And then there is a lifting of this data. So it seems that again, in this minimally wild case, the tropical reduction does not lose any data. And finally, I'll just say two words about proofs. In both cases, we just lift stars in the graph, or maybe in two graphs, yeah, compatible stars. It's easy, it's even essentially unique if we are local enough. The question is about gluing. This is a real difficulty, and gluing is done by classification over annuli. And here I mean the following. Differential form on I is binomial. So this is the gluing lemma, main lemma. Is binomial. That is phi equals to a0 dt over t plus an tn dt over t. This is the residue on A, and this is determined by absolute value of phi, as we discussed. At least n and the absolute value of an are determined by this. So there exists for some, and this for some coordinate t on A. Similarly, degree p cover ax goes to ay is binomial. With these where exist coordinates, so that the f is given by tx to the p plus an tx to the n, and this time these guys n and absolute value of an are given by the behavior of delta f on a. Its slope is n, and its absolute value is related proportional to absolute value. So that's it, and I stop here, and thank you for your attention.